Okay, and welcome to Broken Silicon, a computer, hardware, and gaming podcast. This one a little bit less of the gaming. It's about quantum computing. And actually, let me just start. I'm just going to read a snippet from the always reliable Wikipedia. Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computation. Computers that perform quantum computations are known as quantum computers. Quantum computers are believed to be able to solve certain computational problems, such as integer factorialization, which underlies RSA encryption, substantially faster than classical computers. The study of quantum computing is a subfield of quantum information science. Just some general info. I don't actually know if that will help most people understand what we're about to talk about, but I'll let my guest introduce himself now.
Hi, yes, I'm the quantum computing researcher that will be talking with Toms and try to introduce to you quantum computing and the best of my ability. I'm finishing my master's right now and I will be starting my PhD in September. So This is my background. I mostly work in quantum machine learning. That was, it's a lot of buzzwords as
You've got machine learning and quantum, right? So you've got two of the biggest ones. Again, like we said before we started, you're just missing blockchain and maybe self-driving or something in there.
Well, big data, yes.
Maybe fusion.
It's one of the experts, Nathan Webb, says about when you put machine learning and quantum together, you get hype and hype, but it's not hype plus hype, it's hype times hype. You have hype square.
You know, if this was 2017, we could have made a cryptocurrency, right? And we could have just said, you're one of the lead developers, a quantum computing machine learning researcher. And, that right there would have probably got us into the top 10 shit coins.
Exactly. But if you make a quantum cryptocurrency, you have to call it the Wisner, since he thought about quantum money a long time ago, a researcher in the 60s. And
is he dead now?
I don't know.
It doesn't matter. We would have just said he's still alive and working with us on our website, right?
Exactly. But a lot of his work came out and eventually was dug up from his drawer under his desk, right? Because it applies to quantum cryptography, and a lot of the algorithms of quantum cryptography use the work he did a long time ago.
It's actually so interesting you bring that up. Like someone was working on this and then they found it in his desk. Like and this was a few years ago, I had already been interested in like Bitcoin and stuff. And I thought I would start looking into the cryptography behind it. And I found many of the principles, many of the algorithms used in Bitcoin were pioneered in the 1800s. And then you start reading some of the work of cryptographers in the late 1800s and you realize, dude, these guys had created uncrackable keys before there were even really computers. And how old some of this science really is. How many scientists over the past 200 years had solved, they had the laws of thermodynamics. They could conceive of what a computer would be able to do in the future. And so they had written entire textbooks about how to secure that data and then never got to see anything done with their work really yet. It would be their grandchildren that finally utilized it. I find that so fascinating that finally it feels like we're using some of the stuff that we started figuring out 100 years ago.
Well, in science, we're really standing on the shoulder of giants. We're also standing on the shoulder of science and on and on. But we talked about RSA, but the RSA, it's the initial for the people who discovered it, right? Rivest, Shamir, and Adelman.
And you just said RSA, which for those, to be clear what you're talking about encryption.
Yes. But this algorithm was discovered 4 years before by Clifford Cox, who was working with the British Secret Service. And so it was classified. And he never, his discovery was never known until the late 1990s. And, I remember my advisor talked to me that there was when he received the prize, this person pretty much he was talking about RSA without never giving any credit to himself, as during a talk after receiving one of his prize for his contribution in cryptography.
Well, and you wonder how much research too, especially stuff that has to do with anything that can relate to the military, we don't know about. And I don't mean that in a conspiratorial sense. Like I don't think I don't think the CIA has any secret bases on Mars or something like that. But I'm sure there are small little discoveries that are out there that we don't know about or won't know that we had before for many years. Like there's a lot of evidence, for example, that we had stealth technology so you don't show up on radars long before the stealth fighter jets came out from the United States, like 10 or 20 years in limited capacities. And they just, didn't tell anyone. And like the Enigma machine that cracked the Nazi, code, like they just would straight up let some battles be lost by the Allies so that they didn't know they had that. And there's some theories that the CIA or someone in government may have very, very limited quantum computers already, but that they don't use them because if they did, the cat's out of the bag and now everyone knows. Although actually, I don't think they do. I don't know. We're getting into wild speculation, but I am curious what you think about that stuff.
I don't think they do have wild quantum computers, but they may have some better algorithms hidden somewhere.
Sure.
Maybe they're not quantum or anything like that, but I think it's even if they need to be small, those groups, and if you're too much people, you have leaks. So the scientific community, with its many people, they're competing against them a lot. And in crypto, if you hide your algorithm, then it's not secure, right? The algorithm has to be published to have security proofs and attack being made.
To be battle tested, to be peer reviewed. Exactly. Because if it's not peer reviewed, it's not going to work. That's another. Yeah, actually, you touched on two things I want to say too. Is when people peddle conspiracy theories, and you're like, there's this one small smoking gun. Well, you have to say, well, how much does this actually affect people? Is this actually not a big deal? Is this actually not something a lot of people care about? Because if it's not, well, then maybe it's a conspiracy. Like I believe there are a lot of tiny conspiracies out there. But when something's a really big deal, and especially when your conspiracy involves thousands of people working on it, guys, someone's going to go public. Like this idea that 1,000 people stayed quiet for more than even a few years it's actually kind of ridiculous, right?
Exactly. I mean, after about 100 people, humans have a hard time, keeping track of everything. So even with 1,000 people, even with secret things, you really need to have everything contained, I think, if you want to maintain any sorts of secret at that point. But that may be too much delving into conspiracy theories right now.
Well, yeah, but so that is to say that quantum computing is not just this thing someone probably has already. It's very, very, very new, very unproven. And actually, let's start getting into the direct notes then. So Dominique Koch writes in and he says, hello, what made you want to study quantum computing? And what exactly are you researching right now?
Well, after in Quebec, we have something called Cégep. It's like last year of high school, first year of university. But when I was finishing this, I went to, a talk from my eventual future university I went to that described, quantum cryptography and, purely explained and very well vulgarized about maybe first year bachelor student with a more general education, right? That would be the equivalent for the state. What was quantum computing? And, it kind of sold me, and I went to that university and eventually, made my way to the quantum course. And
what about it sold you, right? So you said you were already in computer science, right? And then you had a presentation or took a class. And what about quantum computing made you say, oh, that's what I want to specialize in?
Well, it was at first I was studying because machine learning became popular, so I wanted to do a bit of machine learning, and then I was like, for quantum computing, the idea of it, and because somewhere in the way, without going to too much detail, the maths between ML and quantum computing are quite similar. Both of them are based on linear algebra, but matrix, vector, and things like that. But we can go into much more details later if it fits the conversation, right? But So from quantum, it's the thing you can do is pretty much having a secure secure cryptography, right? Which is based instead of in general, it's mostly hypothesis, right? We mostly do hypothesis on what we can compute efficiently to make cryptography, right? Or a SYN, things like that.
Right.
It's hypothesis. But with quantum, you have security that's based on quantum mechanics. So your hypothesis is stronger. If quantum mechanics needs to work differently, you need to have a major discovery in physics. So it can be a bit more interesting, even if a major discovery in computer science is also interesting. But it would change the understanding of physics if the most quantum cryptography wasn't secure.
Well, and one way I'd phrase it, correct me if I'm wrong, but you're saying quantum cryptography is you're trying to secure something based on the laws of quantum mechanics, right? Instead of based on the laws of thermodynamics. Well, Joe writes in and he says, well, I've heard that quantum computing is mainly capable of completing calculations specific to the parameters of a problem presented to the computer and is not suited to general computing tasks. Is this true? If so, will quantum computing ever be able to replace a general CPU?
Well, for now, that's what it is true, but it could replace a general CPU because everything you do classically, we can do it in quantum, right? But it comes back to the idea that you just take a general CPU and make it, transform it into everything. So it's reversible, and then you can use a general CPU and make it quantum if you want. But this is really, really far away. You would need a really, really large amount of qubits to be able to just even simulate your basic current computer, right? We're really, really not there. So for now, it's much, much to the benefit to let quantum computers be considered a bit like ASIC, FPGA, or GPUs, right? And use them to solve specific tasks because we don't need it for something else, right?
And I do plan to get into this much, much, much more heavily pretty soon. But the problem I have with quantum is just the immense amount of effort required to even make it run at all, right? And that would really be one of the biggest limits to having a quantum computer as a personal computer, at least right within our lifetimes. I never would speculate on what we're capable of doing as a human race in 1,000 years. Who knows, right? Who knows what we're able to do in 1,000 years? But being able to, cool something to 0 degrees Kelvin isn't exactly a small feat. And I understand that there's theories about how we could solve that, but it's like, well, okay, but do it.
For many applications, you don't need to solve that, right? You don't need to have things run at 4K and, that.
You mean 4 Kelvin too, when you say 4K.
Exactly.
Not 4K gaming.
I was trapped this way when I was visiting some lab, and they were talking about the quantum acceleration. It was this run at 4K, this run at 4K. I'm like, but there's no display. What are they talking about? But yes, it's 4 Kelvin. Yeah, from a general perspective, yes. Right now, you can run things that we'll call them hot quantum computers, but they're not really quantum computers. Just as a opposition to cold fusion.
Mm-hmm. And this kind of gets me to one of my greater opinions that I'm starting to have more and more, I find. Like, again, if you were to talk to Tom 5 years ago, I would have been a bit more optimistic about all this futurism stuff. I would have said, yes, in 2020, we're all going to have self-driving cars, foldable phones, and and then we'll maybe have fusion energy in 2025. And here I am, and I'm like, didn't Paris say they wanted to have their fusion thing up and running by 2021 or something? I don't think they're going to. Where are these self-driving cars? I don't see them. They're out there to a certain degree, but the idea that we're all going to have it, and it's like, we have a folding phone, but do we really have folding phones? I don't know that we do. I mean, not at least with the ease of use and ruggedness that you would want out of it.
Basically, when you use photon and maybe for crypto and for a random number generator, right now you don't have to be at 1 Kelvin if you want those kind of application, right? you can use quantum randomness to have a real random number generator, not a pseudo-random, which suffers from the same problems that other cryptographic algorithms have. It's a hypothesis on computing what is efficient to compute. Right.
Mm-hmm.
Right now, they're currently being done, but what we want is we want to make them. We want algorithms that are like device independent, so that even if your device isn't really good or is maybe in some way it's working against you, then you can even make use of it for quantum random number generator. And for photons, it can be done right now. The Chinese were able to use photons to exchange a quantum key, right? So for encryption, and there are banks working in the British banks working on this that were able to do it. Even US banks are working on this, and right now they're even trying to make it work underwater. Right, some students experimented with trying to send a polarized photon, which are qubits at that point, underwater in their own pool. So I guess it's a good excuse to go swimming this summer.
Well, again, though, it's like, I mean, you're what it sounds like you're saying is there's a lot of things working in experiments right now, right?
Well, for the optical part, it's a bit less of an experiment when you're able to exchange a key and have a video conference using that key to secure it. You're talking about it's experimental, but more on the engineering side, I will say. So the floor more on the engineering side and less on the on everything else, right? It's a question of getting sound engineering, making sure that your hardware is working properly and doesn't have flaw, and eventually it can be manufactured at scale and can be deployed. So I'm a bit optimistic on the cryptography side of things for quantum cryptography, which within the next 10 years, right? I think we will get some.
Right. So you think in the realistic amount of time, we will have quantum keys and be able to crack non-quantum keys?
No, we will have quantum keys, but we may not be able to crack quantum keys. It may come. It may be that what it'll do is that instead of basically you may not be able to do end-to-end encryption, but the way to do it is basically you and the server will be able to exchange a quantum key, and then that server will exchange a quantum key with someone else, or that could be another server, and on and on and on. Right. Instead of using
that's an interesting point, if I'm understanding you correctly, that you seem to be bringing up here, which is that, well, we might not be close to even be able to crack. We might not be able to have the doomsday quantum computer soon that can crack all keys that we have right now, that we already can use. Right. We can already make keys that are quantum computing brute force proof now.
Yeah, but the problem with that a bit is that this replaces mostly the things that the quantum computers don't really break, like SHA-256. It doesn't replace authentication and signature, which is public key encryption, which is RSA. So we replace something that already quantum computers have a hard time enough, but usually it's part of what cryptographers call defenses in depth, is that basically have a lot of different technologies so that each fails differently. It's all Diffie from Diffie-Hellman, which is another crypto system based on factoring, a bit like RSA talked about in a conference recently. But basically, you want to use many different technology in crypto so that if one fails, then not your whole ecosystem is failing at that point.
Well, yeah, and this is a bit unrelated, but this, defense in depth, I mean, another way of putting it is just don't let there be one fail state, right? Like, I mean, what did I read? It was like literally if you just have two-factor authentication with an account, you have like almost a 0% chance of ever being hacked, because now they not only do they need your password and your email address, but then they also need to have access to your phone at the time that they're trying to hack it. And just doing that also probably means they won't bother you because other people don't do that. So once they see you have two-factor authentication, they're like, it's not worth their time. Right. And that's why so much of protecting your data is just not telling everyone what you're doing too, by the way. Like, just if they have to guess, if there's doubt, doubt is so important. Like being able to steal from someone, most of it comes down to knowing exactly what they have to steal.
Well, I mean, cryptography is basically, even quantum, it's not secure if you have somebody looking over your shoulder. So
Yeah. So Jake the Dude 23 writes in and he says, could you explain what kind of use there is to quantum computing? From what I understand, they let you have something like 87 possible states instead of the binary on or off or yes or no answers you can get from a traditional computer. For example, an AI running on a quantum computer could have an opinion on a subject other than just giving a hard yes or no, right? Correct me if I'm wrong, but it seems to me quantum computing will allow us to simulate biological computers much more accurately. Otherwise, I'm not so sure. What really are the uses?
Well, I would correct one thing is that AI on classical computer can have an opinion. And in fact, they often do, which is a bit of their vulnerability. They run stochastic. So they like, when you have, say, when it's running image classification for AI, sometimes it's going to tell you an image is like 50%, it has a 50%, 55% chance of being this image rather, and 45% of being the other image. And you can,
the AI
you can tweak, you can tweak, you can tweak some things to make it so that just without changing much of the image, just changing some color value, shall we say, to make it believe the other way, right? It's a bit, it's an old field in AIs right now about, adversarial example and the way you can, I view it as basically a Rorschach test for AIs, right? You can basically show them image and it doesn't, they believe something that is completely different right now.
So what would you say, right? What would you see as the uses of quantum? Because we're talking a lot about securing encryption and cracking keys, but what
for quantum computing,
can you do with a quantum? Because if we have let's say we have a computer 10 times better than what we have now. With that, I can already think of being able to do quite a lot. Like it's starting to run into me running out of things to come up with that we can't do once we have a computer that powerful without quantum. But what will quantum actually allow us to do that we can't do, that we can't even fathom to do now?
But simulation of biological system is one, right? Basically, when you do protein folding and everything, when you go at that low level, you do need to run into quantum effects. So most current systems, they partially simulate some quantum part and do classical. So yes, for protein simulation and basically what they call quantum chemistry, even right now, the current computers we have are being used for this. They're not really used for a great result, but they are being used because, for experiments, and we need to research and, iteratively start developing new algorithm, new approach at the same time as the hardware gets better to have concrete and good results in this.
So it sounds like you're saying quantum computing should be very, very useful at simulating things.
Yeah, but it's quantum simulation. It's the first application they thought about the physicists. It says we are going to use quantum computers to simulate quantum system, whether it's hydrogen atoms or even molecules, protein molecules. It can be very, very well simulated with quantum computers, much more accurately and efficiently that you can do classically. Because
right, and I think efficiently is the important thing, right? Because right now to simulate systems, we need an immense amount of graphics cards and processors to try to simulate something. And you're saying if we had one really powerful quantum computer,
because it's that exponential. Could run.
Right, it's exponential. So it's not a matter of just, we need to fill up an entire football stadium with computer parts to run one simulation on a protein. Instead, the quantum computer is exponentially more efficient. So it might be better than several. In a lot of application,
yes, especially in simulation. Not in all of it, but yes, it's exponentially more efficient in a lot of application, which is basically factoring. And in this case, quantum simulation, which is, when you tell me I have 10 times as much computing power, I tell you, I can simulate about 2 or 3 more qubits. Because that's what you need if you want to simulate quantum. And the underlying system of Fortune is that it involves quantum physics. So you're only adding maybe 1 or 2 more parameters, right? But with a quantum system, if you make 10 times the number of qubits, then you have 10 times the amount of parameters you can simulate in a more ideal stance, ideal world without
idealized.
Without running into algorithm and error correction.
So I have a question. I'm actually going to skip ahead to this part of the notes I have here. Have you ever watched the show Devs?
No, I did not watch the show Dev.
That's unfortunate. I don't know what you like, right? So I don't know if you'll like the show, but it's basically a science fiction thriller. And I'm going to get into, I do want to bring it up because I think, and based on what other people I've talked to that work with quantum a little bit, they said the show actually nailed it better than than it really has any right to nail the concepts for a Hollywood writer. Like that, the guy actually did some real research, which I always love when that happens.
I tend to not trust Hollywood sci-fi show.
Well, let me. And so I'm going to get into the spoilers, though, right? So just a warning to everyone: there will be spoilers I discuss here. Just because I can't talk about what I want to unless I reveal some spoilers. But basically, the show is what I would say is just your classic kind of secretive AI research company in Silicon Valley, right? That's where the show takes place. And there's a couple of new people who join the company. They have a startup. There's various characters, and they join a secret wing of this company that's called Devs, and it's secretive. It's like their, black research area of the building where they're doing stuff that they don't want their competitors to know about. All companies actually have stuff like this, but they find out that they basically have a working quantum computer, and it turns into kind of a sci-fi thriller because, why are they hiding it? Why do they want other people to not know about it? And at first, when you realize they have a quantum computer, you're not sure what they're using it for. But what you realize through kind of a series of episodes, that's almost like a detective show, honestly, that the main antagonists of this software company haven't just created a quantum computer to do simple simulations, that they're basically trying to put as much data into the of like real world objects and animals, and like scanning animals day after day after day as they decay and die, to simulate the real world. They want to simulate the real world using a quantum computer. And what you slowly realize is if they can simulate this real world, if they can simulate what's going to happen through decay, maybe they can simulate a decision someone's going to make. And then you start to realize, no, they're not even just trying to simulate what decision someone's going to make in 10 seconds. They're trying to simulate the entire world through all history. And again, it's a show, but basically what you find out is that they've made a quantum computer that can simulate real world objects and everything around them. And because they can simulate that, like you touched on before, they can reverse time, not really reverse time, right? Not really, but they can look at what's happened in the past. And so because think about it, right? If you can simulate what's happened in the past based on current physics of the present, that means you can simulate the future. And what you realize is they basically have a window into looking into everything that's happened in the past and everything that will happen in the future. And then it gets into like, questions about if people really have free will, and, all of these questions about multiple world theories too. Like, are we actually seeing what will happen in the future, or are we looking at 99% chance of what is going to happen in the future? It's a really good show. I really do recommend it, right? Obviously, I think it's far-fetched to think they would have this type of quantum computer in like 2022 or whenever this takes place. But, you have to accept the TV show's premise. And they but what it always seems to come down to when I watch or read about these types of things is that quantum computing feels like it's always portrayed as kind of a threat, right? Kind of a threat to mankind, like the atomic bomb. And that's kind of some of the themes in the show too, of like, well, once we have this, it could completely change everything. So what do you think about quantum computing as kind of being potentially a threat to ourselves, right? Okay. If we actually got something this powerful.
Well, I may be a bit biased, but I think quantum computing is a threat to just people who are slow to adopt it, to investigate it. But mostly, I may be biased. It's not me trying to get a job or anything, but it's just that the way I see it is most enterprise who did not 2 years ago start looking into quantum technology or doing it right now, right? And it's maturing enough so that the threat is if your enterprise, which many are dependent on the algorithm that are being used right now for crypto or or any other concept, whether it's even if they do protein folding simulation, that they are expert in that and they are not looking at quantum computing, that maybe those enterprises may just disappear as quantum computing becomes important, and if you don't adopt quantum technologies, that's where the threat is. I don't see it as that revolutionary of a threat, right? It's a bit like saying industrialization was a threat to farmers, right? At that point, it just technology progressed, and humanity has to adapt. And well, if you don't adapt, then your company or your way of life may stop existing, as it were.
But so you see it useful, right, for being used to do simulations for like curing cancer or something. That's what you see it as a productive thing to be used for.
It's going to do simulation on cancer. It can do simulation on small stuff. With this simulating the world, it's a bit too. I don't know. It's too big. It's not even macroscopic for the kind of quantum computer we should have soon. I mean, for most, that's basically.
Right. It's a TV show I'm talking about.
I will quote Scott Aronson, right, when we were talking about the quantum supremacy a few months back, and he said we're in the vacuum tube era of quantum computers, right? We haven't found the transistor yet, so progress will be. It will happen, but it's going to be slow and steady, right, as it goes. But right now, my belief is most promising area of technology is quantum cryptography, and I think you will have quantum cryptography before you will have the ability to break, most keys right now, and so it's a question of adapting yourself to an emergent technology.
Well, that's a really that actually makes me feel quite a bit better to hear you say that. It seems like we will have, shall we say, quantum defenses long before quantum computing's actually able to do any real damage to everyone's, keys and privacy, right?
Yeah.
That makes you feel a bit better. But it is interesting, I think, that you brought up that we are in the vacuum tube era, that we don't even have the transistor yet. Because that part doesn't, but you're saying that eventually we could have these computers capable of projecting people's actions. It's just we're so far away from it.
I don't know. It's something. It's mostly reminding me of Foundation from Isaac Asimov with psychohistory and predicting the history of people right now. I think it's a bit more esoteric. We're not to the point where we can simulate the old world. Like maybe we need a Maastricht brain. Maybe I'm pronouncing it wrong. But at that point, if you want to talk about simulating the world, you should ask Isaac Arthur. You would know more about it.
Well, let me ask you this, though, right? Because I am just curious, and I don't mean to get off subject, but I think it's a fun thing to talk about. Like, so let's say you were in this show I talked about, though, and then you walk into this lab. They don't tell you what it is, right? They just decided, and this is what they decided in the show with one of the characters. Hey, you're smart enough. If you accept this, we're going to put you into our devs team. And that's some of those things everyone's always like, oh my God, I got to get this, massive pay increase. I get to work on the coolest new stuff no one else gets to see. Let's say they said that to you. They said, you are that smart. We're going to put you in there. And then you discovered that they're working on a computer that can project humans' decisions, let's say a year ahead of the time they make that decision, which is actually something they also touch on in the new season of Westworld, by the way, which is very interesting that those shows came out around the same time. But so what would you do if you saw you were working for a company that was trying to simulate and predict everyone's decisions a year ahead of time?
I don't know. The scientific in me is quite excited. So it would be really interesting in how they do that, because it's a lot of software work to do that as well.
Yes,
we shouldn't mind that. Even if computers can double each time, making software that doubles performance, that's really, really hard.
Okay. So you would just be excited, though. You wouldn't be concerned about the implications of like one company being able to control. Like, is that is one thing that I'm a little concerned about, is what if one country or company does get a computer not that strong as the TV show, right? But I mean, even a tenth as strong as that would be insane, right? Like, the amount of power that would give them is pretty crazy, isn't it, though?
Yeah, but it's a bit like the USSR. You were making an assumption with the atomic bomb. When the idea has become, as when someone has gotten the idea working, right? Somebody else is going to copy it, right? Mm-hmm. There's already the groundwork and everything like that. When you have a computer that powerful, they were able to make it work. I mean, it's a lot of hard work. So somebody else is going to say, well, now that we know a bit how they do it, we're going to be able to restore it and imitate it in a way. So I don't see a country having a monopoly on it. If they do, it's not going to be for long. It's not going to be for long, or even just one company. Right? There's already so many competitors in quantum. Right? Even if we come to the situation where it will be at worst Intel versus AMD, right, situation, I don't think there will be that much of a monopoly in the quantum computing.
Yeah, I really don't have that much more to add to this part of the conversation. Because I don't even know, it just feels like the potential of how powerful a computer of this magnitude would be. It's honestly kind of hard to fathom what would change. Mm-hmm. It's just like, it sounds like you agree though, right, that this would be comparable to the atomic bomb, not in terms of making it sound scary. I don't mean to compare it to the atomic bomb to make it sound scary. Just that there would be everything we know about physics before and then after, right? Once we get quantum computers, our capabilities are going to be vastly, vastly superior than before that. Yes. There could be a whole new industrial revolution, frankly.
Exactly. That's the point. But I'm quite an optimist on this. I don't see threat from AIs right now. So, and I don't see much more threat from quantum computers, even though I think quantum AIs, but I mean, that's more of a hope than anything, more of an opinion. I mean, I think those may be the kind of AIs that may be the best to imitate human behaviors at that point. But we won't. I don't think we'll see any of those in our lifetime anytime soon. But
you're saying that's a problem for our great grandchildren to figure out.
Yeah, exactly.
But who knows, what the heck's going on then. But yeah, okay. So I don't know. We've been touching on it a bit. Brian Scanlon writes in and he says, what are currently the biggest challenges associated with quantum computing? I've read that quantum error correction is critically important to ensuring accuracy, given that quantum computers may have a tendency to be noisy, for lack of a better term.
Well, yes, it's noisy. You have decoherence, you have error. So quantum error correction is one of the main area to get, working, large scale quantum computing. But even smaller computers right now, smaller circuits that are currently being run that do simulation, you do quantum ML on those right now. Those have, when you do a bit of machine learning on this and learn some of the gates of the circuit without going into too much detail, those can help correct some of the errors that you have inherent in your circuit right now. So I think for a lot of large scales for breaking, RSA and everything like that, you need a lot of qubits. So those are far away. You need error correction. But there will be application for what they call NIST device, right? Near-term intermediary quantum device. Basically, it's those will not be. Will have to do some, I guess a bit of batch error correction or do it themselves. But those will have application, I think, soon, right? Whether it's on simulation, whether it's on quantum ML. Even right now, they are being used and run to, do experiments and increase our knowledge of how the hardware works, how our software is working right now. So I think those will have a soonish application, even without error correction.
So error correction is the biggest problem right now, though, you would say.
Yes. If you can make, if we could have, basically is that you have a physical qubit, which is the qubit your computer has. And when you start correcting error, you have logical qubit and Morse code. You have 7 in one code and 5 in one code. Basically, you need 5 physical qubit for 1 logical qubit, or 7 physical qubit for 1 logical qubit. That's without going into topological quantum computers, right? But at that point, you will need you have a scale that even if we have right now some computers that are 32, 64, even 128, first of all, they cannot do error correction.
You mean bit?
Qubits, right?
Qubits. Okay.
Yes, sorry. they even cannot do error correction right now because the qubits are too noisy, and you need a threshold so that when you add more qubits into the system, you can run the error correcting code, right? But even if they did, right, the amount of qubits we would have would be something in the order of like 4, 5, or 6 qubits at that point in time, right? And it's not a lot to do anything, right? Your computer right now can simulate a circuit of 6 and 8 qubits really, really efficiently, right? It's not taking that much time if you want to run circuit that small, right?
So how do I put this then? Because from the sounds of it to me, it sounds like right now so much of quantum computing is making it work. Oh, well, of course, right? Because we don't really have that many quantum computers yet, but it's all about making quantum work on standard computers now. Am I wrong?
If you want to do quantum simulation, then you can simulate quantum circuits on current computers, and we can do about 20 qubits on your average GPU. And if you have a server, you can do about 40 to 50, right? With supercomputers, right? That's
and we're doing that,
scaling, right?
Like for academic purposes, right? Though, for like simulating things to try to learn more about quantum computing itself.
Exactly. Yes, exactly. Well, I did it for my research when I did my quantum machine learning things. I wrote my quantum simulator, I coded it, and they did my experiment using this. Right, because you usually don't have access to much quantum hardware, right?
Not usually.
I do have some access, so I have to remind me to use this before it runs out in September. But right, so to do some tests. But basically, the big player right now, you have China, Rigetti, IBM, Google, and Intel. Those, and there are some minor player like 1 qubit, and a bunch of quantum startup like Zaplata and other things like that. But those guys, the big players, they have quantum computers right now. They do offer cloud access, and there are a lot of software solutions. And IBM likes to market a lot their
IBM
solution.
Always markets it. Yeah,
and I mean, but I like we do like the Rigetti solution in my lab. I mean, quite a lot. I mean, so the people who worked on it find it quite useful. But there's Xanadu that makes they're more in quantum AI, but they make an overall course software solution, so you're not dependent on any specific stat. And there's work on quantum compilers even to make the circuit run with any variant of the hardware right now. So there's a lot of development even on short-term quantum hardware, and there's simulation. You usually need both right now to do what you want to do in quantum. You're pretty much, if you have all of the current quantum computer can be simulated, right? And you're probably gonna have a better results simulating yourself most of the 20 qubits. But you will not have what the hardware is doing, right? What sort of error it's having. And everything that goes into the engineering and the physics department that you do when you run a real circuit on the quantum hardware to improve our knowledge of how to make better quantum computers physically.
So, but again, though, right? So most quantum researchers are just trying to understand how to build and improve quantum computers. Most of the research is into making them, right?
No, there's a lot of the research in physics. Right,
okay.
Into making them, and it's much more into engineering right now. I would say that it was 5 years ago, right? The hardware we have now, it's a lot more engineering, right? If you were 5 years ago and you had you wanted to do quantum engineering, it basically did not exist. Right now, it's existing and it's working. You can go into do engineering and work with your screwdriver and try to make the machine work. Right? It's a huge candlestick, they call it, right? That works at like 1 Kelvin, depending. And
so, Carbon Cry writes in though, and he says, "But will it play Crysis?"
If you wanted to play Crysis, maybe in 20 years we can do quantum Crysis. To please the gamer, there are quantum algorithms for ray tracing and path tracing, and it's going to be. And if you add one, right? Right now, if your GPU was quantum right now, basically some sort of 1650 was quantum, it could run ray tracing quite well.
So, but then he continues and he says, how does it feel to be working on Pixie Dust? And he means it as a joke. But when I was at Hot Chips last year, someone asked about quantum computing and Jim Keller cut them off and said, that's Pixie Dust. It's nothing. So what do you say to that though, right? Like, so Jim Keller at least openly says quantum is alchemy. It's like trying to turn lead into gold and it's never going to go anywhere. What would you say to that?
Maybe that's the reason why Intel fired him. They didn't believe in Intel's quantum department, I guess.
You're going to get so many angry comments now from all the fanboys that will say, no, Jim Keller left Intel because Intel's stupid.
I don't know. I don't have a sense on this, I think. But Jim Keller is quite brilliant. So, but he's in classical. He works in classical computing. So,
do you think there's? I mean, obviously, you're going into quantum, right? And so you're biased. We agree,
exactly.
Right? But at the same, you're convinced. But at the same time, would you give, I don't even know how to ask this, right? Would you give any shred of credibility to Jim Keller's side of the argument that maybe it's not going to be used that much? Do you just entirely reject that? Could you see some situation where in 10 years we're like, hey, we're going to use it for this stuff, but it's not going to be used in nearly as many things as we thought we would?
I'd say 5 years ago, yes. 5 years ago, it was Pixie Dust. So maybe it didn't keep updated, but the development in hardware is quite crazy, right? We went from, we don't have any working computer to we're in the vacuum tube era, right? It was fast, right? Basically, like from like 2014-15 to right now, right? Basically 2015, the Chinese launched a satellite. IBM had their first quantum computer working with on 5 qubits. And, right now we've been having shall we say, a Moore's law for quantum computer where we doubled the amount of qubits every 1 to 2 years, right? At that point. So, I mean, when I first thought about joining quantum back then, right, it was nowhere close to what it is right now. And I mean,
so you did think it was risky.
Faster. Yes,
you thought it was risky to join it before, though. Was it a hard decision at first?
A bit, but I'm like, I have a bachelor in computer science. I can work other computer science job, whether it's in machine learning or whatever. I mean, as long as I don't work in web development, I'm fine. I just hate it. I didn't do my degree for this.
Yeah, I think I study mechanical engineering, as you probably know, and I mean, I did some programming there. There were some things that I thought were fun to work on, but I agree. If I went into programming, I think web development is the one thing I would just not want to do. Although I'm not trying to throw any web developers under the bus listening. I'm sure there are some. But yeah, well, let me move on though to another problem I have. And I think I touched on it, but I really want to push into this. And that's the fact that and I don't even completely understand this, right? I'm not a quantum researcher, but as far as I'm aware, all of these quantum computers need to run at sub 1 Kelvin, just so most people who listen to this probably know what that means, but that's negative 273 degrees Celsius. That's almost absolute zero. Am I wrong? Don't they build these in cold areas too? I swear I've heard plans to build quantum computers on the South Pole of the world, just because at least it's colder there, and so the facility will be easier to cool further. Like that, it takes an immense amount of energy to cool them. Or am I wrong about how hard that is to cool them? How much of a problem that is?
Yeah, it's hard to cool them, but it also doesn't replicate, right? Basically, from what I remember is that if you have a quantum computer and you cool it, and then you decide to, okay, now the machine needs maintenance, so we're going to uncool it, and then you rerun the same machine, it's no longer going to be calibrated, no longer going to have the same kind of errors, the same kind of behaviors that it had previously. So yeah, it's hard, and you have to cool them right now, but as I've said, for quantum cryptography, you don't need to cool it, right? So there's an application out there that you can do at room temperature, right? But for most of the exciting quantum stuff, I guess, if you're not excited by having key that are secured by quantum mechanics, right? I mean, it's your point of view, but Yes, for that, you need to cool it, and you need classical controller at those temperature, and it has challenge, right? For example, we talked a lot about HBM, right? But HBM at 102 Kelvin, the way it stacks, right? When I was talking to people that make memory, right, it doesn't like this temperature. It's mostly gonna fail and breaks, right? So there was some recent article with Intel making a quantum controller to work at those temperature, right? So there's a lot of challenge, even making classical hardware working at 1, 2, and 4 Kelvin, depending on which layer you are on the cooling stack, right? Because when you have those quantum computer, it's basically like a chandeliers, right? You have when you have in your room, right? The cooling goes to the tube, right? Like a use like each candlestick has cooling, and each layer has different temperature. From like 10, 4 Kelvin to 1 Kelvin, right? But this is what I know. I'm not really in physics and in engineering. I'm more in computer science. So I usually just assume properties of this.
Well, so that's where I keep approaching it from too. Is it's like, for me, it's not the complexity of the computer itself necessarily, although that's certainly a whole thing. I'm an engineer. I just want to look at the thermodynamics, and when I see that you need to cool this at absolute zero, it's like, like I start to think about it like, for instance, like I don't think there's any way we're putting quantum computers on a spaceship ever, right? You have to worry about radiation coming through the side to hurt humans. These machines sound...
You're sure. Because satellite have less noise to worry about, because the atmosphere makes a lot of noise. So when that's why the Chinese launch a satellite. So they have more coherence, right? For like 90% of the travel, when you shoot it from space, right, your qubits, you won't have decoherence because you're in space. So maybe space is a better place to put the quantum computers. Who knows?
I was actually arguing the opposite.
I know.
But I mean, like, and just when you think of how much energy is, well, and I guess I don't know that, like how much energy is needed to power one quantum computer at IBM. Do you know off the top of your head?
No, I don't know off the top of my head. I don't. Maybe IBM probably told me and I forgot.
I wonder if Google will just tell me. Let's see, 25 kilowatts of power, $25,000 per unit. When you consider how much energy those Cerebrus wafer scale things are using, it's not that much energy, I guess, if you could actually make this do the things we want it to, I suppose. But I mean, I guess that's kind of how I see... I don't know. I'm very skeptical now, as you can tell. And so I guess the way I see quantum computers is kind of how you said in the beginning, kind of like ASICs or FPGAs, where it's like, I don't, in our lifetime, see these things replacing personal computers or doing a bunch of stuff. I just see them as, man, if you've got a lot of money and like a really expensive facility and a really specific problem, this quantum computer could maybe allow us to solve a problem we just couldn't solve before. But it's not really there to replace classical computers, right?
It won't be. I mean, most people don't like talking about hybrid computing when you have a classical computer and a quantum computer working in tandem, because for them, when you have a quantum computer, you need a classical controller anyway. So it's part of the feature of a quantum computer is to have a classical computer assisting it basically at that point. So yeah, it will... For quantum computing, it will devolve into it will evolve, I would say, into ASICs and FPGA, right? Style quantum, and you can view it the same in the same way for like when we could use optical quantum computing for the application I've mentioned before, quantum cryptography, because you can send photon to current optical fiber, right? You can share quantum key with this. More work is needed to make it mainstream, but that there will be application that don't need to run at room temperature, and the people in physics and in engineering will do their best to make a quantum computer work at more acceptable temperature, right? So eventually, maybe, but it's not coming anytime soon that will get room temperature quantum, and there's a big breakthrough, and I would be quite happy if there was a big breakthrough like that.
Well, so that's perfect you bring that up. Kerry Baldino writes in and he says, mainly curious where quantum computing is at now and how it compares to current microprocessors. Also, what is the estimate on your side for quantum computers becoming attainable for personal use? So where are we now And where will we be, just by wild guesses from you, in 10, 20, and 100 years?
Well, where we are now, I refer again to Scott Aronson. We're in the vacuum tube era, right? We don't have the transistor. In 10 years, I would say personal use is going to be over the cloud, right? I dislike anything that's over the cloud, but that's basically what the first quantum computer will be, right? It will be over the cloud, right?
Like paying for it, kind of like how we do now for server processing power over the cloud. Do you think that's where we'll be in 10 or 20 years?
Yeah, in 10 years. In 10 to 20 years. That's good. That's going to be it. You can already
It'll start to become commonplace
you can already
in a college,
pay
right?
for quantum
That's what you're saying, though? Like you're saying, just to completely define what you're speculating on, you're saying in 10 years, it'll be commonplace for many STEM researchers at college to go to several different types of quantum labs and use their processing power through the cloud.
Right now it's common, but it will be even more common, right? There's enough, maybe not for STEM lab, but right now researchers are using it, right? Some researchers are using it, and if you have specific users, but it will be, shall we say, more widespread at that point.
So in 20 years, college students can use it.
You can use it right now. IBM will let you use their quantum computer.
Well, that's what
I've used it before.
I said STEM researchers.
Okay.
I just meant like anyone in engineering, computer science, or...
Okay. Well, you can use it right now. I mean, in Sherbrooke, right? The University of Sherbrooke, back near home, has working chandeliers, but their quantum computers have 1 or 2 qubits, right? I think they help ST Micron. It's ST Micron that fab some chip for them that can handle 1 or 2 qubits at something like 1 or 4 Kelvin, right? They're working on quantum dots. I won't go into too much detail because it's basically physics at that point. And it's not my area of expertise, right? But right now, a college student can work on some hardware if you're interested in the engineering and the physics kind of things. You can find work opportunity there, and I would say it's already somewhat common. But when you were talking about STEM researcher, I thought maybe there will be some biologists, chemists already working there. Those may be in 10 years because it's basically a bit similar to the machine learning development.
Well, they're included in STEM, but
we're not right to the point where they are using it, right? Unless they're working in the quantum chemistry on quantum or doing 14 folding. You need to be very, very in their area of field, and they have someone there that does quantum computing, and they decide to collaborate for articles.
Okay, so my brother Dan, who's the co-host of every other Broken Silicon episode, who's in genetics research, in 10 years he'll be able to use quantum. You think is what you're saying?
I think it's hopeful, but that it would be great for him if he was able to do that. I mean, for protein folding and everything, it would make for some great development in genetic research.
Telos writes in and he says, will quantum computing truly change the networking landscape, or will it be a more gradual phase change? I've heard both argued in my college days.
I don't see how it's an opposition, though. I mean, it will truly change and it's going to be gradual. So I
guess, I don't know. Maybe he's asking, is there going to be small uses here and there, or is it just not going to be useful and then change overnight?
I think it's going to be small step. We're going to test small step and come to the point where most of the cryptography is use quantum key distribution. Well, hopefully, right? Hopefully, and the sooner the better, because it's one less thing that can be broken, right? And it's basically the defense and depth arguments again.
Archon 971 says, I always wanted to know, if you decide to study quantum computing, are you being taught about a general system and how to build it so it can be used universally? Or are there major architectural differences dependent in which field a quantum computer should operate? Furthermore, was your studying more theoretical and limited to several tasks that you can do with a quantum computer, or did you get a chance to work on a project? So I don't know. There's a lot of questions there.
There's a lot of questions. First of all, I would say we have a general system, but it's basically a bit like a classical computer. You have like high-level programming language, and then you have a low-level programming language, like from Python to C, C++, to the low-level assembly, and to the machine code that your computer has. Each of those has a specific layer in classical, and in quantum we have the same thing, right? We have usually how we study it is that we make abstraction of the error correction at first, right? we work on like an high-level perspective of quantum, like just using circuit with perfect qubits and everything. And the more you go down, the more each architecture has different things. And it's what most quantum computing language, I would say, or libraries try to abstract. Each of them tries to be able to, so that if you have a circuit right now you're working and you want to run it on a quantum hardware, it can work on any quantum hardware. You can run it on the library, and it's going to compile it the same way we would compile C++ code to assembly, and it would be a bit like difference in architecture between x86, x64, x86 32 bits, and RIM, right? If you have the same software, you want the compiler to be able to compile it for different architecture and whatever the features are. So we can be hardware agnostic this way, and we learn the more general approach. And if you want to delve into specifics, then it becomes, again, a question of engineering and physics.
But it is more bigger picture theoretical
exactly.
for you right now.
Well, when I began, it was mostly fully theoretical because we didn't have quantum hardware when I began studying quantum computing. Right now, we have quantum hardware, which is, we didn't expect this, right? So it's for me, it makes me more optimistic about the future. And it became a much more, you can have much more practical thing. And yes, I did get a chance to work on on the project when I did my master, which was in quantum machine learning.
To move on to another subject here, this is kind of one of the last ones I actually wrote down. What are your thoughts on, because this is a big thing. Well, it's a big thing for some people. For me, I actually, as you can tell, kind of dismiss it in these notes for now. It's not to say that I entirely dismiss quantum computing and the ability to hack into, like SHA-256 and all of that. I just don't see it as this fundamental threat right now. And it's something that kind of, correct me if I'm wrong, but you basically said that we have ways of securing quantum keys right now. And so before we're ever going to be able to hack any Bitcoin key, we will have encryption that is...
The problem for that is that, as I've said, is that our quantum key, they replace the thing that quantum computers don't really break, like SHA-256, which becomes SHA-128.
Which Bitcoin uses.
Bitcoin uses, but Bitcoin also use some elliptic curve to do the signature, the authentication, to make sure you're the one who is paying for it. And what he said in the video, I think, is that for this, even if it's broken, if you only use each address once, then
that's right. That's what I've heard from someone else too.
Right. Look, I don't know. I mean, I've watched the video. I think
it sounds like you understand how Bitcoin works more than most people I talk to. So I don't know how in depth you would be able to get into this conversation.
I'm more a Monero guy. So
oh boy,
I prefer the anonymous things. But yeah. I think you were a Monero guy since you were mining with Vegas a while back. But
oh yeah, I mined some Monero for sure. I did, and although I did. Hey, look, man, I don't know how much. I mean, I can talk about Monero, Ethereum, and Bitcoin as much as you want. I think you know from listening to me that by now I've thrown out the other coins and I'm just all in on Bitcoin at this point. But, and we can certainly get into that if you want to. But I mean, well, let's just say this, though, to round up the thing I brought up, though, it's that, I mean, look, for the most parts of Bitcoin and many of the cryptocurrencies, which almost all of them are derived from Bitcoin anyways, they're not easy for quantum to hack, even theoretically. Now, there are certain signatures that aren't as encrypted, right, as the other keys. But at the same time, like if you like you said, if you use a different public key, because the way just for everyone listening, understand this, the way a Bitcoin wallet works is you generate, most apps do this by default, a new public key when you want to receive Bitcoin. All quantum could do is theoretically eventually take a little bit of time to crack one of those, is what you're saying, right? And they would have to know that. And if you use a new one each time, there's no way they could get to almost any amount of it. And there's right, for all intents and purposes, there's unlimited public keys there could be. So the ability to crack it now is not easy. And most developers, the ones I follow, the ones that actually seem to know what they're talking about, right? That talk about it say that they've already kind of started work on what they would do to patch it if they
there's
needed
already
to.
work. I think the NSA has each year they want to make a post-quantum cryptography, right? If we want to talk about crypto, we talk about post-quantum crypto, which is basically a signature algorithm, right? That at that point is not breakable by quantum computers, right? That's what they are trying to develop, right? Whether they'll be able to do it right now. Because basically at the beginning we were considering two algorithms, RSA and Michaelis, and RSA was eventually broken by quantum. Michaelis isn't right now, but we don't really know, right? But we don't know if it's broken. So the consideration in post-quantum is basically if we add up an algorithm, could it be broken classically even, or will it be broken even by quantum computers in the future? So it's an hard decision. So that's why the NSA is working on this, and with people all over the world are working on making on post-quantum cryptography using very, very different kind of technologies for those interested, whether it's different elliptic curve or learning what errors or a bunch of technology that's pertinent to go into details. But because even quantum has that weakness, because the weakness of quantum is that we don't have a quantum scheme to sign and authenticate. Basically, is that the money problem is that you want to give your public key so that you give in Bitcoin so that you receive your money, but at that point you want to authentify the other people would want to know if the money is giving is in fact you, right? That's the point of signature and public key crypto, right? You want to authentify that you are yourself, right? When you're with someone, and that's the thing we don't know how to do in quantum right now, and that's the thing that is currently being broken, right? It's authentifying that you are the right person, and if you want to do a Skype conversation, whether it's a Skype conversation that the guy you're talking to
Skype conversation.
Yes, exactly. For example, the guy you're talking to is the actual person. We don't know how to do that quantumly, right now. Maybe we'll know in the future. And classically, it's what's currently being broken. And it gets it more extended when you're at a website, whether it's a Steam and you want, Steam and you want to play a game, right? You would like to know that you're sending your money to Steam and not someone else, right, at that point. So changing public key all the time for Steam may not be a good solution for them, right? For example, you want a certification or what for whatever website you're using your money at.
Well, that's kind of something I point out too to the people that say quantum's a threat to cryptocurrencies. Is it's like, hey, look, if Bitcoin's already partially quantum resistant, so if they find a way to break Bitcoin with quantum, I got news for you. They've broken everything. Everything we own is now broken and was probably broken years before that. So I think the canary in the coal mine will be when other things start getting broken first, right?
Yeah, but at that point, like if cryptocurrency are broken, your credit card is broken. You have other things to worry about, right?
We've officially gotten off subject. So how about we just do some final reader mails here? Let me see. Which outcome of quantum computing do you think will most affect the types of computations gamers care about? Quantum computing being used directly to simulate quantum mechanics in a game, or accelerating classic things that we use to run games now? So in other words, he's saying, and let me add on to Edward Huff. This is Edward Huff who asked this question. How soon do you think we will use some portion of quantum computing? And I don't know, I don't want to be dismissive, but like real quantum computing in a game, and what will we use it for in a game?
I think if I'm all for multiplayer game, we're going to use quantum key distribution for the server-side communication. That's why I'm all for the most, but that's strictly quantum computing. So, I mean, for gaming, it's really you're asking things a bit too far, right? It's a bit how shall I put it? It's a bit like asking what is machine learning going to help game with?
Right? What everyone wants to know, though.
In 2005, right? But in 2005, right? Like when people were bashing a neural net, right, as something that will never work, right?
Yeah, that's it. So you're saying, I mean, look, everything will probably be used in games eventually, since so many people play games, but it is definitely not the first, second, or third thing, right?
Yeah, well, it's already said path tracing, retracing. You can accelerate it with a quantum computer if I remember the algorithm properly, right? But for us quantum computers, we're not. I mean, it can make some a cool blog post somewhere. Here's how you accelerate, the Monte Carlo search, but we don't.
That's enough buzzword to get some clicks, right? Quantum ray tracing in gaming, and everyone, all the scientists and the gamers want to click on that link now.
Exactly, but it's not the most of our research is not concentrated there because it's somewhat far away. It doesn't have major real world application, shall we say? But for networking, I'm hoping we switch to quantum encryption soonish.
So to make sure I understand correctly and summarize for everyone, you're basically saying quantum computing gaming is not even in the top 3 things on the list, but once we get to gaming, it'll probably be used for network communication and then ray tracing.
Yeah. Well, maybe not then ray tracing. Maybe there's going to be more interesting stuff you can do with it at that point. I mean, it reminds me a bit of we're going to talk about Naughty Dogs. Maybe it's a naughty subject right now, but there's this really, really good blog post by one of the making of Crash Bandicoot, right? By the developers. It's really, really great for every classical computer scientist, right? The devs of Crash, right, pretty much talks about how they were working with the PlayStation, and I don't remember, I think it's 8 or 16 megabytes of RAM, and all of the optimization, right? They were working to make Crash Bandicoot fit on a PlayStation 1 and on a disc, and it's really, really, it's really.
I think I've heard of this book before. Like that, there are so many blog posts. Like the principles used to make Crash Bandicoot actually were like a really, really good outline of like all of the classic problems you run into making games and programming, right?
Mm-hmm. And at that point, I'm sure if we would have given those people quantum hardware, they would have done something with it. We would have no idea, right? I think the best example I had was they had to compress things, right? So they were using some sort of a huge $50,000 workstation machine that pretty much did some sort of gradient descent to compress everything, right? So they had to tell artists that the character they made, if it didn't converge, right? If they weren't able to find a compression for it, you need to change your character because we cannot fit this on the 16 megabytes, I think, of RAM the PlayStation adds. I mean, it's hardware consideration all the time. If you give them the tools, they will use it.
Yeah. And so here's some final reader mails. And some of these, I don't even know if I understand. Edward Huff writes in and he says, macroscopic decoherence, yay or nay?
And I saw it when you saw me the note, and I don't even know what he's talking about. Right? That's
I think we're going to give that a nay.
I know decoherence. What is decoherence, right? So I mean, you when you fight decoherence with error correction, that's what we want to do, right? And macroscopic, I guess. So yeah, when computer gets bigger, you need more error correction. But I don't really know what he's talking about. So I'm pronounced. I don't know.
Lazy Physicist writes in. And he says, what kind of qubit do you see as the most promising one for future quantum computers, especially for scaling to larger numbers and lower operating costs? So let's ask that one first. He has 2 questions.
Well, I think, and a lot of physicists talk to me about it, the technology for future quantum computers hasn't been invented yet, right? But if it has, I'm on the topological quantum computers. That's the side I'm on for now, but we'll see what happens.
Okay. And he says, how do you rate the chances of finding a job in the field in the near future? I'm currently doing my bachelor's in physics.
Yeah, well, right now, most people says if you want to go into quantum, right, it's basically you do your major in physics and your minor in computer science. In a few years, you'll do the reverse. But me, I went with just computer science, no physics. But it doesn't really matter.
That makes a lot of sense. Yeah. Yeah, and that's kind of how it always works out, right? Like once something's new, it's more on the physics and engineering side. Like, let's see if we can even build this goddamn thing. And then the more you get into it, it turns into, well, can you operate it, right?
Exactly. But if you have a bachelor in physics, I think maybe a master's still needed right now. They're looking to, I think most enterprise says we have too much PhD, we need more master's students, probably because they want to lower their costs a bit. But right now, I would say yes, you will find a job. It's basically, I hope, right? I'm a bit optimistic. It's basically what's the likelihood of finding a job in machine learning in a few years when you're in 2008 or 2009? You're gonna somebody is gonna hire you. So there's many enterprise working on this, right? We've talked about them: Rigetti, Google, Intel, IBM, One Qubit here in Canada. But even in Montreal, we have many startups, even in Quebec. But there are people that are working internationally. Singapore, the National University of Singapore has a huge lab there, so there are people working in quantum. Even in Korea, people are working in quantum. In China, many people are working in quantum. I think, without going into too much politics, but China pretty much in the last 5 years went from being at the bottom of the barrel to being the first in quantum. So they're the one with the most money.
So let me ask you that. What would make you say that China is the first in quantum?
The amount of money they have invested, right? I think, basically in quantum computing.
Do you mean first in spending money, or have they done things with it?
They've done a lot of things with it. They've spent money, and they've done a lot of things that were mainly. Most of the things they've done, it's something Canada, the US, and even Europe. They had plans to do it. They just didn't have the money to do it, right? So, which is why they went from because it was mainly an engineering effort right now. You had to construct the satellite. You had to construct all of the device that works with it. So it make them go from they I guess without going into too much detail, they've taught algorithms that may have been developed in the West and everything, but they've implemented them in practice at scale we didn't have before when they have implemented quantum teleportation or quantum cryptography as they did. I think they're right now. I think they're the first, right? Because look overall, but the West is first in quantum computers hardware, right? China, I would say, is first in globally in mostly quantum encryption because they really want, for some reason, I would say they really want to have a secure infrastructure on their side. I wouldn't put my money on why.
I can guess why. Yeah. They don't want to have their little Black Mirror surveillance state dystopia they've built for themselves to be hacked. Not to say that I have any opinions on that, I clearly do. But it would make sense that the first thing they want to do is make sure no one can hack them.
Yeah, but most of the scientists, to be honest with this, we're kind of neutral with this. Chinese scientists, they collaborate with Western scientists. There's not many animosity, but science a bit come first, right? Well, I mean, for the, I guess, the people who want sciences, they'll be the judge of whether it's good or bad. I'm a scientist, so I'm on the side of good, but...
let's build it. Yeah.
But the Chinese lend their satellite to Europeans from time to time when it passes over them, right? To do experiments and things like that. So there's a spirit of collaboration in quantum. I don't know if the Cold War right now...
It hasn't been ruined yet, right?
Yeah. We'll ruin it, but yes.
All right. I have one more reader mail here by Jeremy Lamb, and he asks, are we living in a simulation?
There was a great opposition to that some people at my lab worked on, but basically
okay, I'm curious.
Basically is that when you code a simulation and everything, you're going to have bugs, and so there's basically two things. Either it's the bugs will break the simulation, or the people will figure out they're living in a simulation, right? That's the two main things. But when you start, basically, one of the main arguments for living in a simulation is that you can make simulation in a simulation in a simulation, a simulation section. Right?
This idea of multiple worlds, but inside a computer.
Yeah, but at that point, this idea is a bit broken because you have this factor of bugs and you add the factor of a problem in the universe that is doing the simulation, whether it's an electron flipping a bit.
Exactly. I was about to say the amount of energy it would take. And they touch on that again to bring it up in the show Devs, where they're like, well, we could do this. And he goes, you would need a universe-sized computer to simulate the universe 100% accurately. And then someone said, that's not true. And then she goes, it is true. Literally. That's how big the computer would need to be to simulate an entire world, an entire galaxy or universe 100% accurately.
Yeah, it's a bit at that scale, but exactly. But you have errors, right? Your computer, you would have to use supernovas as coding, because if you have a supernova that's happening and it wipes out your computer, that the simulation run out and the simulation is over, right? So basically, it adds and compounds on the risk that the simulation will break. So at that point, the conclusion is we're not living in a simulation, or in the unlikely event that we do, we're living in the higher level on the simulation section.
Or at the very least, we're living at one of the highest tiers of a simulation, is what you're saying.
Yeah, exactly. Because if we assume no fancy new physics, right? That the simulation, our simulation is they have the same physics as us, right? Because if you start changing the rules of physics, then I guess you can do anything you want at that point.
I don't know. You say there's no bugs in the world right now, and I look at current events. I'm seeing a few bugs. There's a few glitches going on, if you ask me.
Maybe it's human
or maybe
malware.
We're just learning a lot about human nature in the past
maybe
few
it's
years.
Human malware, but we won't. Yeah.
Yeah, my answer to the simulation question is this: it doesn't matter, and I don't know why you care. Whether we're living in a simulation or not, how does this affect you? This is whether the world's real or not. This is the world you're living in. Your actions matter to the world you're living in. And you should try to live your best life and take it seriously, because whether it's a simulation or not, this is the world you got. So I don't know why you care if it's a simulation. Why does it matter? I don't get it. I don't. Maybe okay. So say we're in a simulation. What changes? Nothing. You're still living in that same house. I don't.
Maybe you can break it or some things like that. But yeah, I'm on your side now. Right.
Yeah, I don't. So many times when I hear, "Are we living in a simulation?" it just reminds me of people who say they're not religious but are creating a religion. It's like, well, it sounds like you're trying to create a religion to make the world make sense to you, and maybe you should just accept you don't have any control whether it's a simulation or not.
Isn't that what ideologies are, though?
Yep. Ideologies and religion are the same thing. It's just sometimes people don't have a religion, and so as we're seeing, they commit to certain ideologies a little too hard.
It's a bit like the West. What was the allusion? You were on the book 6 or the 7 in the fall of the Roman Empire or something. Sometimes it feels like this, right? Well, but maybe we're going too out of subject right now.
Well, if we're talking about the Roman Empire, I think we're several tiers out of subject. Yeah.
If you get me talking too much about history, it's not a good idea. It's a bit of an idea. But I'd say I would find more job in quantum than in history. So I'm in quantum.
Well, yeah, probably a more lucrative job too, most of the time as well. Well, that's basically it then. That's all of the reader mails. I believe that's all of the subjects I wrote down. Yep, I crossed them all out. I guess this is pretty much it. We should wrap it up. But I mean, is there anything else you want to plug or say about anything you're doing? Probably not, but I mean, maybe if you do. And otherwise, is there any last things you want to say about quantum?
Maybe I wanted to explain a bit more on because I'm going to steal someone else's analogy, right? Diffie from Diffie-Hellman again, on what exactly, how does a quantum computer break RSA as a final conclusion for the people who have stayed after watching at 1.5 or 2 or 2.5 or 2 speed right now? But right, so basically his analogy was RSA is basically it's a racetrack, right? It's the way it works is that you have a racetrack, and what we can do classically is we can go in the racetrack, we can move ahead in the racetrack fast, quickly. That's what we know how to do fast. But in order to break RSA, what you want on the racetrack is to go to the step you were right before, right? Right before you were before, right? Go back. But we don't know how to go back efficiently, right? Basically, in a racetrack, if we want to take a million steps, it's basically it takes us 30 more times than doing one step. And if we want to go a billion better steps, then it's 60. It's how he explains it, right? What happens is that the thing that is secret right now, it's the length of the racetrack. Because if you know the length of the racetrack, then you can make as much step as you need to come back before. What the quantum computer does, right, basically, is that he can find the length of a cycle. So what the quantum computer pretty much do is that the so-called superposition parallelism is that he's going to take every position you can have on the track, right, and put them in superposition, right, this way. And basically at that point it becomes finding the length of a cycle, which for the technical viewer we did it to Fourier transformation, but without going into detail, this is what we can do. We can find the length of the racetrack with the quantum computer. And it's why we can break RSA and the Diffie-Hellman scheme, right? That's the thing, because it becomes a cycle, because you go back and around, a oval on a circle, depending on which racetrack you like the most. It's a really good analogy, and it's I find that it really explains to maybe more layperson what the quantum computer does. Right? It's basically we can find the length of the racetrack with the quantum computer. What classically,
right? To try to see if I can understand what you're saying. You're basically saying right now there are so many problems where our only solution is to throw more computational power at the problem, exactly. Right? We're just throwing more at it, and it's because we have no clue how much it's going to take for us to finally get the right answer. And even if we get a right answer, it's like, well, we could probably have the answer be more right. And what quantum computers do is you put in more of the variables, and they can actually get you kind of at least some of the parameters you're trying to solve for. And so, once we get quantum, if we use it for specific tasks in conjunction with powerful classical computers, there are just some problems we're going to be able to solve that we couldn't solve before.
Exactly. But there's limits when we talk about quantum parallelism, right? Still a bit of the technical things, right? It's something I wanted to touch on. Well, we talked a lot about being in superposition and parallel. So basically, if you have one qubit, you're at the same time 0 and at the same time 1, which, amplitude of probabilities, but we're going to do that with some likelihood of when you measure it, obtaining 0 or 1. But one of the limits with that is that for one qubit, the amount of information you can extract is 1 bit. So basically, you have your qubit right there that's in 0 and 1. But when you measure it, you will only get one of the option, right? You will not get the whole information on the state, right? That's a limit of the quantum computers. And when you see fancy talks about quantum computers that usually are hyperplex, they kind of don't understand that even if you have, say, 10 qubits and you would have 2 to the 10 possibilities, right? Because it's exponential at that point. The only information you can extract from it is 10 qubits. So it's a lot of hard work algorithmically to be able to manipulate the amount of data you're putting there to extract in 10 qubits the answer you want. Right? From 10 bits, because it's really, really hard work this way. So this was the small bit, I guess, some of the small technical explanation I wanted to give people that state. So I think it's going to be all for me.
No, that was very good to put at the end there, just kind of in many ways making it more clear, I think, how it'll be useful and why some people probably dismiss it as they don't understand, frankly, what it's actually useful for, right? Just like machine learning.
But it's the same with machine learning. From my side, I do a lot of quantum simulation, so a bit like the AI guy, I'm starving for memories, as we talked on. I mean, but I think his memory problem at worst quadratic. Mine is exponential, so I need more memory than he does. Activist content with 80.
You mean in a graphics card? Probably in everything, right?
In everything.
Would 128 gigabyte graphics card be enough?
It's a good start. It's a good start
because I know Intel's working on one right now, by the way.
Oh, that's nice. But
you're saying that's just a start. You're like, could you make it 256?
But basically, it's each time you double the memory, I basically have one more qubit I can simulate. That's basically how it goes, right?
So there's no limit, though. Make it a terabyte while you're at it.
Yeah. But it's to the point where, when you have GPUs that are handicapped in memory, at that point, even if the CPU is slower, right, they can just run things because that's access to more memory without you having to make TensorFlow do some memory swapping between the RAM and things like that, right? It becomes a bit more complicated if you want to code things properly at that point.
Okay. Well, I mean, I'm going to be honest. We've clearly moved through multiple things where I was just at the limits of being able to understand it without reading a whole textbook beforehand, at least.
I viewed it a bit, contacted you a bit because it was an exercise for me to vulgarize better.
And half of it is, and Dan says this all the time, is just being able to convey the thoughts is half the struggle, because most people don't go to grad school, so you need to be able to tell them what you're actually doing.
Exactly. My advisor, my master's advisor, was really good at that, and it's something I'm attempting to try to be. Right, but it's hard. It's hard.
That's the difference between a great and excellent, or between an okay and an excellent professor too. Is if the professor, like you could have a professor that's not actually as brilliant, but if he actually knows how to tell you what you're studying. Man, I've had some professors that were clearly geniuses, and they just couldn't even. They couldn't even tell me what we were doing. And then you have some where it's like, oh, now it's easy.
I don't know. You want them to become, I think, what's the point when they don't really do course or only graduate course? I think it's faculty there in the US, right? So at that point, they only specialize in research, and don't have to get
a lot involved. Of them, yeah. And so they don't have time, or they don't care. Right. Sometimes they just don't care. They're only at the university to do research, and they're basically only teaching because, well, they have to keep their job. And they'll just show up and read a chapter from a textbook in front of everyone, close it, and walk away.
Yeah, usually those you want to see them limited to like graduate course with 6 people, right? Or
so at least everyone can ask questions and work on it hands on.
But it's usually 6 people that are interested, so they speak the same language at that point.
Oh yeah, that's true too. Yeah, so that they don't have to actually teach that much. It's mostly just application, anyways.
Yeah, exactly. We had our share back home of a teacher that really, really didn't want to teach the course. But a few of them were honest. They tell us at the first course, I don't want to teach the course. I'm forced to do it because there's nobody else.
That's what I've heard too, is that nowadays they often just tell you that. They're like, you're on your own, by the way. Well, I do want to thank you for coming on. I don't really have, I guess I'll just say this at the end of the episode too. A reminder that the people submitting reader mails, our patron supporters, the patrons are the ones making this possible. If you support us, you can get these podcasts early and ad-free, and also submit questions and concerns about all the content being worked on in the reader mail, and it will help develop, and you can have it asked to guests as well. So just remember that if you have the extra scratch. Otherwise, I don't know. Any last words, any last things you want to say, anything you want to plug before you go?
No, I don't have much to plug. I could complain about the challenge I had in my simulation to work things on AMD, but the AI guy did most of the complaining, right? So maybe if we complain enough,
it's worth pointing out. So I guess we'll say you're plugging AM disasters, and but joking aside, that AMD still has a lot of work to do in the professional product stack for this type of work as well.
Yeah, basically our CM, the solution they have for basic machine learning doesn't support complex number yet, and I've verified, from the GitHub, and it's a bit unfortunate. I wish they would.
Yeah, there will be a link in the description for everyone curious. ROCM, I watched AMD's little video for it, and it looked like a cryptocurrency ad, didn't it? Like, it looked really, really cheaply made and like general. Like, no offense to AMD, but like when I watched that, I was like, I feel like I'm on a Tomcoin website or whatever my cryptocurrency would be called.
I know the development slowed down last year because the guy who was maintaining got hired by Intel. I think he had.
Everyone's hired by Intel right now.
Strangely enough, he was complaining publicly about Vega 10 in the GitHub. About he wanted to add it to his. I think it's going to be in a chapter in the black book of GPUs. If he writes some memoir on trying to make code work for it. It's a bit funny. But yeah, it's I find it unfortunate because AMD GPUs have more memory, so I'm on the side of the more memory. I wish they would work, but yeah, it's.
I hear this is what they're gonna try to fix, both with adding more memory and having better professional and more specific driver support with RDNA too. So that's all I can add. is that all I've heard are great things about RDNA2 for everyone. Although, and I think it's probably true. It's just at a certain point, I almost get tired of saying, RDNA2 is going to be great, guys. I still don't know that much about it.
Well, right? I hope so. Yeah, but I hope so.
I hear it. I mean, I really do hear that it works well at these types of things you're talking about. It's just, well, we'll see. What do they have? Probably.
I'm probably going to get the GPU from both NVIDIA and AMD, and you use the one that does the training the best as training and use the one that does it the most for gaming at the same time.
Yeah.
Because yeah, when I like to keep my computer working.
Yeah. Well, okay. That's about it then. I'll say thank you for coming on. Thank you to everyone for listening. Subscribe, share, like, and yeah, I don't know. I'm sure we will talk again. Have a good evening.
Thank you. Have a good evening.
Bye. The following podcast was brought to you by the YouTube channel and website Moore's Law is Dead. Moore's Law is Dead and Broken Silicon are trademarks of their creator, Tom. That guy is me, and I am indeed the creator, editor, writer, and showrunner of Moore's Law is Dead podcasts, videos, articles, and other media. However, Moore's Law is Dead is a team, with Broken Silicon co-hosted by my brother, Dan, audio editing by Gerard Cortez, and select technical editing by Carbon Cry. You can find all of our information, including how to get a hold of us, at www.mooreslawsdead.com. And if you are a fan and would like to send mail or other hardware, please mail parcels to Moore's Law is Dead, P.O. Box 10468, Peoria, Illinois 61612. And speaking of fans, without exaggeration, the patrons are solely responsible for the continued distribution of the content you just listened to. And so if you have some extra money, but only if you do, please consider supporting us. For just $2 a month, you get access to the exclusive podcast Die Shrink, voting on subjects of future podcast episodes, the ability to have your questions read aloud on Broken Silicon, Die Shrink, and Loose Ends, and of course, the Moore's Law is Dead Discord full of like-minded people who would love to meet you. I am one of them. The Discord is only at $1, and at higher tiers, you get access to ad-free episodes of Broken Silicon, the back catalog of Flyover States podcast, thanks in the credits of videos and podcasts, and other perks as well. And if you cannot afford to support us, please just share Moore's Law is Dead videos and podcasts with friends and family on social media and Reddit. And give Broken Silicon and Flyover States a 5-star review on Apple Podcasts. All of this really does help so much more than I think anyone realizes. If you'd like to advertise on the podcast or a person of interest who would like to be a guest, please reach out to the email address mlhbdead@gmail.com. But as I said, this podcast would not be possible without its fans supporting it. And so now it is time to give a personal thanks to the greatest of the fans. The following supporters are at the 10 gigahertz or higher producer levels. Bootman, Carbon Cry, Dean, Benny Berlin, Justin Yant, Thomas Rupp, I Love You, Lynn and Jim Bollocks, Joshua Albin, Muhammad Al-Kawari, Frederick Lau, James Crasta, Justin Parrish, Zachary Martin, Terrence Herod, Brad Medlin, Phil S., Thyrus, or the Ninth Dude, Greg Renegar, TSPCFS, Crisentine, Night Rogue 77, The Mechanical Philosopher, Lebo King Kilo, Fatboy Diesel, Daniel Hyde, Matthew McMullen, Christoph Novak, Jack O'Neill, Matt Salem, Aaron Close, Sexy, VI Pass, Sadler, Richter Cohagon, Elethros, Telos, Hey There's a Kitty, Greg T. Wanchuk, Jacob Barber, Exoti, Hector Santana, Matthew Lane, Paul Jones, Jan Rauner, Robert Ducks, Drita Full, Allie Robertson, Eric Jackson, Jonathan, Job, Evan Dingle, Dominic Koch, Dominic Duerk, Original Ross, Wayne, Sam MacArthur, Total Silo, Sol Kanar, Michael Costa, Andrew S., Blake, Aaron Keith, AJ Klein, Endless Loggins, Tom Sanfilippo, Justin Brennan, Ivan K., Trevor Powers, Garrick Scholl, Elenia, Joshua Staveness, Daniel Nishbal, Franco Frederick, Hardware Numbers, Alex Carastillo, Dark Rain 2049, Leighton Perry, Neil X01, Carlos Valdez, Carnivore Bear, and Carrie Baldino. And of course, thank you to Sahara for the music.